All right, so after we talked about the law of conservation of mass, we talked about the need for balancing chemical equations to have the same number of atoms on the reactant side as we do on the product side. So for balancing chemical equations, as we discussed, at the end of this reaction that we were using for the last video, we have 2 iron ions and 3 oxygen ions present in iron 3 oxide. So to get that, at minimum, we need to have 2 iron atoms and 3 oxygen atoms combining together to form that compound. Right now, the way the chemical equation is written, right, we have the formulas for iron, we have the formula for oxygen gas, both here. We cannot change those formulas in any way because then it wouldn't be iron metal and it wouldn't be oxygen gas. What we need to do is figure out how many iron atoms and how many molecules of oxygen are needed to combine together to get the ratio of iron and oxygen ions necessary for iron 3 oxide. Clearly from this, we see that we're going to need multiple irons, we're going to need multiple oxygens in order to reach the iron 3 oxide compound that we need for this product. Our goal is to figure out how many of each of those we need to do so. There's a lot of different ways you can do this. Some of you will find this pretty easy in terms of kind of doing the math and visualizing it off the top of your head. Some of you are going to need to draw it out. So I'm going to start by just drawing it out for the first one or two, and then as we go, we'll look at how we can do this a little bit more mathematically, and you can choose whichever model best suits you. At the end here, we currently have 2 iron ions and 3 oxygen ions in one compound. Right? So we cannot change that compound. It has to have 2 irons and 3 oxygens. We're starting with 1 iron on the left, and we have 2 oxygen atoms in this compound. Again, we cannot change that formula in any way. In order to get my 2 iron atoms that are on the right, I need to have at least 2 iron atoms on the left. So I'm going to add that one in. Now, in order to get my 3 oxygens, I need to have 3 oxygens here. The problem with that is I can't just add 1 oxygen because this formula is O2. So by default, I can only add 1 more of those molecules, but that brings me up to 4 oxygens. And now there's too many on the left and not enough on the right. So that means that I must be able to make more than 1 of these iron 3 oxides. So again, I'm going to make that compound, putting it inside my little bubble there to make sure that I don't change the formula in some way. Now by doing that, it brings me up to a total of 4 irons on the right. So I'm going to need to have 4 irons on the left. And I have a total now of 6 oxygens on the right side here, which means I can have another pair of oxygen molecules to get my 6 oxygens on the left side. So now if we add everything up, I have 4 irons, I have a total of 6 oxygens, I have a total of 4 irons here, and I have a total of 6 oxygens there. So this reaction is now balanced. Now the way we represent this in the chemical equation is by using coefficients in front of the numbers to tell me how many of each of these molecules I needed, or atoms. I needed to write 4 sets of iron atoms here. For the O2 molecule, I have 3 sets of those. And in doing this, I was able to produce 2 sets of iron 3 oxide. It's giving me a ratio here of 4:3 for my reactants, and then that makes 2 units of my product. If I do the same thing for the second one, there's a trick to these ones. If you're able to recognize that there's carbon and hydrogen, and it produces carbon dioxide and water, the trick is to always do the carbons first and then the hydrogens second. If you don't remember that, you can do it in any order, but it's just easier if you are able to recognize and practice doing that. Going through, I'll start by doing the same way I did on the previous one, where here we have C with 4 H's, and that is 1 molecule. I have O2, which is 1 molecule. I have CO2, which is 1 molecule. 2 H's and 1 O for 1 molecule. If I start with the carbons, as I suggested, there's 1 carbon atom present on the left, there's 1 carbon atom present on the right, so that one matches up. There's currently 4 hydrogens on the left, there's only 2 on the right, so to get 4, I would need to have a second molecule of water. And in doing that, I see now that there's 2 oxygen atoms on the left. There's a total of 1, 2, 3, 4 oxygens on the right now currently. So to get 4 on the left, I would need to add another molecule of oxygen gas there, which gives me a resulting final formula, now that all of those atoms match, of 1 CH4. So I can either put a 1 here or I can leave it blank. Usually when it's blank, we assume it's a 1. 2 oxygens, 1 carbon dioxide, and 2 water molecules. Gives me a 1-to-2 ratio for my reactants and a 1-to-2 ratio in my products. If you want to draw these a couple out as well, you can kind of pause and take a moment to do that, but to look at this a little bit more mathematically. In this third example, we have, if we can identify it, a series of ionic compounds. Right here we see our metals. We can probably see some of our polyatomic ions that we recognize. And when we have a reaction like this, which is a series of ionic compounds, it's often easier to treat this by balancing the ions themselves rather than all the individual elements. It still works out, it just takes you longer to do it. But on the left here, I see that I currently have 1 calcium, and there's 3 of them on the right. So I could start off by putting a 3 here, because if I have 3 calcium chlorides, then there would be 3 calcium ions. By doing that, if I have 3 of this compound, I would have a total of 6 chloride ions. And on the right, there's currently only 1 in there. I cannot put a 6 here, because that would not be the formula for potassium chloride. What I can do is have 6 of those potassium chlorides. By putting a 6 there, it also means that I have 6 potassium ions in my products. And currently there's only 3 on my reactants. So to get 6 potassium ions in the reactants, I would need to have 2 of this compound. That also means I would have 2 phosphates, which already matches my 2 phosphates. Gives me a final ratio of 3 to 2. For my reactants, and I have a 1-to-6 ratio for the products. You can also do ratios of reactants to products of like 3 to 1 or 2 to 6, etc. And then for our last example, again, I noticed that there's a carbon and hydrogen compound producing carbon dioxide and water. So I'm going to remember the trick of doing my carbons first, hydrogen second. 3 carbons in the start. So I need to get 3 carbons on the products. 8 hydrogens at the start. So I need to get 8 hydrogens on the products. Then lastly, let's look at total oxygens. From here, I currently have 6 oxygens. And from here, I have 4 oxygens, which gives me a total of 10 oxygen atoms on the product side. On the reactant side, I currently have 3. Now, the problem with this is that there's no way for me to make a 3 into a 10. What you can do is if you get into a case like this where you would need to have an odd number of oxygens, or where you have an odd number of oxygens, you can double all of the other compounds, and then it would work out. So what I mean by that is, for example, right here in our initial compound, it's currently a 1, right? The imaginary blank 1. I can make that a 2. I can make my 3 into a 6, make my 4 into an 8. By doing that, all of the carbons and hydrogens are still balanced. Right? 2 times 3 is the same as 6 times 1. But if I look at my oxygens, I am now up to 12 on the left, plus another 8 over here, for a total of 20 oxygens. And I can get 20 on the left side, because right now I have 2 here, which means I would just need 18 from this one, and I can get that by doing a 9. For our balancing chemical equations, right, these numbers give us the ratio of atoms or molecules to each other. However, in the lab, we're going to be dealing with lots and lots of atoms at any one time. So remember that we've also talked about using the term the mole to represent a really large number of atoms or molecules or ions or anything. So the same way I had in the previous examples a 3-to-2 ratio for calcium chloride to potassium phosphate, which told me that I would need 3 formula units of potassium chloride for every 2 formula units of potassium phosphate. If we scaled it up larger, I could say 3,000 formula units of calcium chloride for every 2,000 formula units of potassium phosphate. And if we scale it up even larger to molar quantities, I could say 3 moles of calcium chloride is equal to, or reacts with 2 moles of potassium phosphate. Right, so another example here, going back to our initial iron and oxygen reaction. 4 atoms of iron for every 3 molecules of oxygen can also be said as 4 moles of iron metal with 3 moles of oxygen gas.